In the last class, we saw that the eigenvalues of a Hermitian operator are real and the eigenvectors corresponding to different eigenvalues are orthogonal. Right? So these things we discussed in the last class. We also saw that the eigenvectors of a Hermitian operator form an orthonormal set. Right? So we can construct an orthonormal set out of the eigenvectors of a Hermitian operator. This, we can call it an orthonormal set. We also saw that this set is complete. We just mentioned that this set can be used as base kets. Okay, these eigenkets can be considered as base kets because they are complete and it's orthonormal. We can use them as base kets. Now, in quantum mechanics, the base kets that we use will invariably be the eigenvectors of some Hermitian operator. Okay. We have seen that the normalized eigenkets of A form a complete orthonormal set. Okay, what was A? A was some Hermitian operator. An arbitrary ket in the ket space can be expanded in terms of the eigenkets of A. So, since the eigenkets of A form a complete orthonormal set, we can expand any arbitrary ket in the ket space in terms of the eigenkets of A. All right. In other words, the eigenkets of A are to be used as base kets. Okay, so it's the same thing as saying that we can use the eigenkets of A as base kets. Okay, or the set of eigenkets of A can be considered as a base set. Okay, or a set of basis vectors. In much the same way as a set of mutually orthogonal unit vectors is used as base vectors in Euclidean space. Okay, let's talk a little bit more about Euclidean space, because we can understand many things by comparing it with the Euclidean vector space. So we have said this several times. In the Euclidean space, we can use three mutually orthogonal unit vectors as base vectors. This means that any vector can be expanded as ax x hat plus ay y hat plus az z hat. All right, so this x hat, y hat, z hat are called the base vectors. Ax, ay, az are called the components of a vector along these three mutually orthogonal directions. All right. Now, we can write this in a slightly different notation for convenience. We can write x hat as e1 vector hat and y hat as e2 vector hat and z hat as e3 vector hat. All right. So we can write the set of mutually orthonormal, or we can write the set of orthonormal base vectors as e hat I or ei hat. Okay, this is a set. This is a shorthand notation for the set e1 hat, e2 hat, e3 hat. All right. Now the orthonormality condition can be written like this: ei vector hat dot ej vector hat is equal to delta ij. This means that if these are the same base vectors, then it is 1. If these are different, it's equal to 0. The scalar product is equal to 0. This is what we mean when we say that this is an orthonormal set. This is an orthonormal set. Okay. All right. So in this new notation, and also we can write ax instead of ax, we can write a1. We can for ay we can write a2, and for az we can write a3. Right? Now, if we write it like this, we can write a vector is equal to sum over I equal to 1 to 3 ai ei vector hat. Okay, so I have now expanded a vector in terms of the base set given as ei hat, ei vector hat. These are unit vectors. All right. Now this ai is called the component of a vector along the ei direction. All right. Now it's easy to generalize this, because now if you want an n-dimensional space, you just have to sum over I equal to 1 to n. All right. If it's a complex vector space, these coefficients can be complex. So in the same way, when we said that the eigenkets of operator A forms a base set, that means that we can expand any vector, right? Any vector, ket alpha. This is any vector in the ket space, or this is any ket in the ket space. All right. So just like we expand a vector in terms of the mutually orthogonal or mutually orthogonal unit vectors e1 hat, e2 hat, and e3 hat. In the same way, we can expand any ket alpha in terms of the eigenkets, ket A prime. Okay, so we say that this set forms a basis. This is a basis set. Okay, so ket alpha can be written as, so let's say there are some expansion coefficients, one for each base vector, right? One for each base vector. Here we say that there are three expansion coefficients. There's a1, a2, and a3, one for each base vector. Similarly, we can write this as ca prime ket a prime plus ca double prime ket a double prime plus ca triple prime ket a triple prime, etc. This is one way to write it. Okay, it goes on like that. Now, if there are too many base vectors, we can instead use the notation C1 ket A1, C2 ket A2, C3 ket A3, etc. Okay, maybe we'll put a bracket here to follow the notation given in the textbook. All right. So if there are a number of base vectors, we'll be using this notation. We'll write it as ket A1, etc., or ket AI. All right. Or in general, we'll be switching between these two notations. So we can write ket alpha as, so this can be written as sum over I ci ket ai, right? Or we can also write as ket alpha is equal to sum over a prime c a prime ket a prime. All right. So this means that you are summing over all the eigenvectors. All right. You are summing over all the eigenvectors in the base set. All right. So in the set of eigenkets. So this summation has to be understood as a sum over all the base kets. Okay, or we can think of it as sum over all eigenvalues. Okay, so for one eigenvalue, you will have one eigenket. We are not in this case, all right. In the case that we have discussed so far, for one eigenvalue, you will have one eigenket. Okay, so you can also think of it as a sum over all possible eigenvalues. Okay, which means that corresponding to each eigenvalue, you will have a number here. Right? Or corresponding to each eigenket, you will have a number here. These are called as the expansion coefficients. These Ca prime, the set of numbers Ca prime, are called the expansion coefficients. Okay, expansion coefficients of the ket alpha in the basis or in the base set, denoted like this. All right. So this is the kind of language that we'll be using. Now this expression you can think of as a generalization of this expression that we are familiar with from the Euclidean vector space. In the Euclidean vector space, these expansion coefficients are real. In the complex vector space that we are talking about, or in the ket space, these expansion coefficients can be complex. That's one generalization. The other generalization comes from the fact that in three-dimensional Euclidean vector space, we have just three base vectors. In this case, the number of base vectors is equal to the number of eigenvectors of operator A. Or in other words, the number of base vectors here is equal to the number of different eigenvalues that the operator A can have. Right? So the number of eigenvalues of operator A defines the dimensionality of the vector space that we are using. Okay, because we are talking about the space of all possible measurement outcomes, and we said that measurement outcomes are eigenvalues of Hermitian operators. Okay, so the space of all possible measurement outcomes has a dimensionality which is equal to the number of measurement outcomes. Okay, so this is why we are using we are using a space whose dimensionality is equal to a number of eigenvalues of operator A. Okay, so we are talking about a space of all possible measurement outcomes. All right. Okay. So here is what we have. In the three-dimensional Euclidean vector space, we can write A vector as sum over I ci ei vector hat. Okay, there is one expansion coefficient for each base vector. Right. Now, what about this expansion coefficient ci? Right. So what we can do here is that you can take the scalar product with ej vector hat. You take the scalar product or dot product with ej vector hat. Okay, let me write it here. So if you try this, ej vector hat dot a vector is equal to sum over I ci, this is a number, and this vector comes inside ej vector dot ei vector. Okay, this hat shows that these are unit vectors. Right? Now we said that this is an orthonormal set, which means that this is equal to delta ji. Okay, this inner product between two base vectors is written as delta ji. This means that if it's the same vector, the inner product is 1. If these are different vectors, the inner product is 0. Okay, this is what we mean when we say that the set EI is an orthonormal set. Okay, so this is equal to sum over I Ci delta Ij. Delta Ji. Okay, symmetric. So let's be careful anyway. This delta Ji. Right. Now you sum over I. Right? But in this whole summation, you actually have to take all possible values of I equal to 1 to 3. Okay? But in this summation, there's only one term surviving because every other term is killed by this delta Ji. The only term surviving corresponds to J equal to I. So when you carry out this summation, every other term will be 0 except for the term where I is equal to J. So this is simply Cj. Okay, so you see that Ej vector, or we can say that Cj, the expansion coefficient corresponding to the base vector Ej hat, can be written as Cj is equal to Ej vector hat dot A vector. All right, or in general, Ci can be written as Ei vector hat dot A vector. Now this is easy to understand. Ci is the expansion coefficient of A vector along the Ei direction. So how do you find this expansion coefficient? This is the component of A vector along this direction. To find this component, you just project this vector in this direction. So if you have a vector like this, let's say this is the E1 direction. All right. Now, how do you get the component of A vector in this direction? You just project it on here. So the projection is the same as taking the inner product. So E1 dot A vector will give you the component of A vector along the E1 direction. All right. In other words, it gives you how much of the vector A vector lies in this E1 direction. All right. So how much of A vector lies in this particular direction? Okay, that's one way to see that. All right. Now these things we are familiar with. We can do the same thing in the case of the ket space or the complex vector space also. So let's do that next. So maybe I'll do one more thing. We can write this A vector now. Before going to complex vector space, let's finish this Euclidean vector space. This means that A vector can be written as sum over I. This is Ci Ei hat. Okay. What is Ci? Ci can be written as Ei hat dot A vector. This is Ci. Okay, and then the direction Ei hat. Okay, so the vector A vector can be written as sum over I Ei dot A vector Ei hat. All right, this is the expansion coefficient Ci. All right, now this is something, these things we are already familiar with. Now the same things can be done in the case of complex vector space also. Okay, let's do that next. So in the case of complex vector space, what we have is, case of complex vector space, we said that any ket alpha can be expanded like this. Okay, we can write ket alpha is equal to sum over A prime C A prime ket A prime. All right. Now, in the case of the Euclidean vector space, what we did was we took the inner product with the dot product with the base vector. Okay, we can do the same thing here. Let's find the inner product with, let's say, A prime. All right, or A double prime. Let's multiply. So in the case of A vector, what we did was we took the inner product Ej vector dot A vector. All right. In the complex vector space, the same idea is denoted like this. We are multiplying by bra A double prime on the left. Okay, so this is like taking the inner product. This is the same thing as projection. Okay, we have discussed this. So let's push this bra A double prime from the left. Okay, so A double prime alpha is equal to sum over A prime C A prime bracket A double prime A prime. Okay, because these are numbers. So the bra just goes in, does not affect these numbers, and then it hits this ket. Now it forms a bracket. All right. Now this is equal to sum over A prime C A prime delta A double prime A prime. Okay. Again, the summation, the only non-zero term corresponds to A prime equal to A double prime. Here A prime is a summation index. Okay. So the only non-zero term here, because of the Kronecker delta, corresponds to A prime equal to A double prime. So this is equal to C A double prime. Okay. C A double prime. Okay. So what do we have here? We found that bra ket A double prime alpha is equal to C A double prime. What is this? This is the expansion coefficient of alpha in the direction A double prime. Okay, so this is the expansion coefficient, or this is the component of alpha in the direction ket A double prime. So these are base vectors, ket A prime, ket A double prime, etc. base vectors. And what does this say? This gives you the component of ket alpha in the direction ket A double prime, in the direction of this unit vector. Okay, or it tells us, in other words, it tells us how much of this ket alpha lies in this direction. Right? How much of ket alpha lies in this particular direction. All right. Okay. So this says that in order to get the expansion coefficient along the expansion coefficient for corresponding to a particular ket, what you have to do is that you have to take the inner product with the corresponding bra. Okay. So this means that if you want CA prime, what you do is that you project ket alpha in the direction A prime. You project ket alpha in the direction A prime. Okay, so this means that our ket alpha can now be written as we write this as so instead of C A prime we have got bra A prime alpha. This is C A prime. Okay, oh, I forgot there's a sum over A prime. Right, I'm just writing the same expression. I'm just writing this expression. This is C A prime. All right. Now we shall be careful, as we said earlier. Okay, the associativity does not apply because this is a number. This is bra A prime ket alpha. So I'll just write it carefully. This is bra A prime ket alpha multiplied by ket A prime. Okay. All right. So if you want to make this, so since this is a number, right? Since this is a number, you can write it on this side, and then the multiplication is legal, right? So then we won't need this bracket and this dot, all right? Actually, in some textbooks, we write this expressions like this without this bracket and this dot, okay? Because we know that this multiplication is not legal anyway, so we don't combine these two objects, all right? But in the textbook that we are following, they are careful about writing such expressions. Okay, now since this is a number, I can put it to this side. Okay, this is a number, this is a complex number, so I can put it to this side. So we get the expression for alpha. Ket alpha is equal to sum over A prime. Okay, I write this ket A prime first, and then this number A prime alpha. I am allowed to write this without a bracket or a dot because this is an allowed multiplication. Right? This is a legal product. Right? So we can use associativity. So this you can think of as ket A prime being multiplied by a number, or you could think of this as operator bra A prime ket A prime acting on ket alpha. Well, you can think of it in any which way, and it doesn't change. Okay, this is the associativity axiom that we discussed in the last class. All right, so that's what I have here. I have ket alpha is equal to sum over A prime, and then sum over A prime, bra A prime, ket A prime, alpha, ket alpha. Okay. All right. Now, as we mentioned, this is analogous to an expansion of a vector V vector. In real Euclidean space, V vector is equal to summation over I, EI hat multiplied by EI hat dot V vector. Okay, so here they have given V vector. We wrote it in terms of A vector in the previous slide. Okay, we said that A vector is equal to sum over I, EI vector hat dot A vector. All right. Maybe it's better to use V vector for the Euclidean three-dimensional vectors because A we are using for operators anyway. All right. So I hope you don't get confused by this. Here A vector is a three-dimensional Euclidean vector. Okay, or it's a vector in the three-dimensional Euclidean space. All right. And the A in the previous the simple A written like this was an operator. This was a Hermitian operator. Okay, so I hope you don't get confused. Now maybe I should have written instead of A vector I should have written V vector. That would have avoided some confusion, but anyway I hope you don't get confused by this. Right? So where the set EI hat form an orthonormal set of unit vectors. We now recall the associative axiom of multiplication. So what did we have in the previous slide? We had ket alpha is equal to sum over A prime, ket A prime, bra A prime, and then alpha. Okay. Now you think of the associative axiom. This term, right? Sorry, this is ket A prime, bra A prime, ket alpha. Okay. This can be thought of in two different ways. Okay. You can think of it as a number multiplying a ket, or you can think of this as an operator acting on ket alpha. Okay. So this can be regarded either as a number bra A prime ket alpha multiplying ket A prime, or equivalently as the operator ket A prime, bra A prime acting on ket alpha. Okay, these are equivalent ways of interpreting this expression, right? Now, because ket alpha in equation 2 is an arbitrary ket, we must have. So this is the equation we have. The equation 2 I'll write here. We had ket alpha is equal to sum over A prime, ket A prime, bra A prime, ket alpha. All right. So we have got an alpha here, ket alpha here. We have got the same ket alpha here also. Right. Now this is true for any ket in that space. This is true for any ket, which means that this thing appearing here, this operator must be the what do you call this? The identity operator. This must be the identity operator. The identity operator will denote as 1. Okay, remember, this is an operator. All right. So since on the right side we have got ket alpha, on the left side also we have got ket alpha. Okay, so what's happening here? We have got ket alpha and something acts on ket alpha and you get the same ket. If something acts on this ket alpha, you get the same ket, which means that this something must be the identity operator. Okay, so identity operator I'm simply writing as 1. Right? So 1 on the right hand side is to be understood as the identity operator. All right. Now this equation is known as the completeness relation. Very important. All right. This is very important. This is known as the completeness relation or closure. All right. So this says that this actually is this statement actually says that the set of eigenkets is a complete set. All right. The set of eigenkets of a Hermitian operator is a complete set. Okay. That's why it's called the completeness relation. Because if the set of eigenkets is a complete set, then we should be able to expand any vector in this form. All right. Now, if you are allowed to expand any vector in this form, then whatever appears here must be the identity operator. All right. Right. Now it is difficult to overestimate the usefulness of equation 3. Right. So it's difficult to overestimate this. So this is very important. So I say it again, it's very important. All right. So even if I say it several more times that it is important, it's very important, I wouldn't be overestimating. Right. So I repeat, this is very important. Now, why is it important? Because we have got an expression for identity operator. We have got an expression for identity operator. Right? So this is something that we do often in physics. If we get stuck with an expression somewhere, all right, we can multiply it with 1, we can add 0, etc. Right? So we get a nice form for 1. We get a nice expression for 1, which you can insert wherever you want. Right? If you get stuck, you just insert an identity operator there. All right. So this will be very helpful. This trick will be very helpful. Okay. So given a chain of kets, operators, or bras multiplied in legal orders, we can insert in any place at our convenience the identity operator written in this form. Okay. For example, let's say that we have got an expression like this. This is a legal multiplication, right? I could insert a ket here simply, just like that. I could insert a ket there. I could insert, not ket, sorry. I can insert an identity operator here. I can insert another identity operator here. All right, and then look at the expression. We'll see that we get some nice way of representing these operators and kets. Okay, that's we'll come to that in the next class, maybe. For example, let's consider this bracket alpha alpha. Okay, let's consider bracket alpha alpha. Now we can write this as bracket alpha identity operator bracket alpha, because it's identity operator. It does not change this ket or it does not change this bra. All right. Now what I do is that I write this identity operator in this form that we had in the previous slide: sum over a prime, ket a prime, bra a prime. We said that this is equal to the identity operator. So let me be careful here and put a dot here and here. Okay, and here I have ket alpha. Now if I look at this sum over a prime can be pulled outside because this alpha has no a prime index and this alpha also has no a prime index. All right, so I can put the summation outside. Now if I look at these things, these are actually legal multiplications. Okay, you can combine a bra with a ket, that's allowed. Here again there's a bra and a ket, so we are allowed to write this, or we are allowed to use the associative axiom and simply write this as bra alpha ket a prime, bra a prime ket alpha. Okay, now again I can write this as we have bra alpha ket a prime. Okay, bra alpha ket a prime can be written as bra a prime ket alpha star. Why? We had this property beta alpha, bracket of beta alpha is equal to bracket of alpha beta star. Okay, and then I have got bra a prime ket alpha. What is this? This is actually the component of ket alpha along the direction a prime. Okay, or this is what we denoted earlier as CA prime, and here what we have is the complex conjugate of CA prime, or this is CA prime star. All right. Now let's we know that these are complex numbers, so we have got a complex number here and then multiply it with its own complex conjugate, right? A complex number multiplied by its complex conjugate. So let's look at complex numbers for a moment. We usually denote this complex numbers as z equal to a plus ib. The complex conjugate is defined as this is a minus ib. Okay, the imaginary part picks up a minus sign, and then we say that this is the complex conjugate. Right? Now, if I take z star z, right, you see that this multiplication will give us a square plus b square. Z star z is a square plus b square. Right? We see that this is positive definite. Right? We see that the complex number multiplied by its complex conjugate is positive, unless the real part and imaginary part are zero. Okay, but we are not talking about such complex number. For a general complex number, this is positive definite. All right, z star z is positive definite. So a complex number multiplied by its complex conjugate gives you a positive real number. All right. So using this, this is also denoted as modulus of z square. Okay, this z star z is also denoted as modulus of z square. So modulus of z square is a square plus b square, and it's positive definite. Okay, so using this notation, I can write this as sum over a prime modulus of the complex number bra a prime ket alpha square. All right, so that's what we have written here. This incidentally shows that if ket alpha is normalized, all right, ket alpha is normalized, then the expansion coefficients must satisfy. So let's look at this thing. All right, so this is actually, we said that this is the component of alpha along the direction a prime. This is what we denoted as mod c a prime. So this expression means that sum over a prime modulus of c a prime square. Okay, this is bracket alpha alpha. All right. Now, if bracket alpha alpha is equal to 1, which means that if these are unit vectors or if these are normalized vectors, okay, then bracket alpha alpha is equal to 1. In that case, we can write sum over a prime modulus c a prime square is equal to 1. All right. So this incidentally shows that if ket alpha is normalized, then the expansion coefficients must satisfy sum over a prime modulus c a prime square. Okay, this also can be written as sum over a prime modulus square of bra a prime ket alpha. Modulus square of bra a prime ket alpha. Okay, these are the same thing. This is what we call as c a prime. This has to be equal to 1. All right. Now this again, as we mentioned several times, this is important for the probability interpretation of quantum mechanics. All right. So I think we'll be discussing this later on, but I'll just mention it beforehand. Okay? I'll mention it in advance so that we get familiarized with this concept. In quantum mechanics, if you have a physical state alpha, we know that kets represent alpha. Sorry, kets represent physical states. Okay, so if you have a ket alpha, you can ask the question, what's the probability? And we know that we can talk about the observable denoted by A, and we know that the possible measurement outcomes of these observables are eigenvalues. Okay, now you can ask the following question: given the state alpha, given the state ket alpha, all right, you are measuring the operator A or the observable A on ket alpha. What value will you get? What value will you get? All right, then quantum mechanics says that we cannot say this thing for sure, but we can say that if I measure observable A on ket alpha, if I measure observable A on ket alpha, then I'll get one of its eigenvalues. I'll get one of the eigenvalues of operator A. All right. What's the probability for getting a particular eigenvalue? What's the probability for getting a particular eigenvalue? Quantum mechanics says that this is equal to modulus Ca prime square. Or we can also write this as, in order to find the probability for a particular eigenvalue, quantum mechanics says that, so we know that this modulus Ca prime square can be written as bar A prime ket alpha modulus square. All right. So in order, this rule says that in order to find the probability of finding a particular, of measuring a particular eigenvalue A prime of the operator A, right, what we have to do is that you take the corresponding eigenvector, you take the eigenvector corresponding to this eigenvalue, project the given state onto this eigenvector. Okay, project the given state onto this eigenvector and take the modulus square, and this will give you the probability for measuring an eigenvalue A prime. All right, this is just a rule. All right, you have to remember this rule. We'll be repeating this thing, all right, so that we'll become more familiar with this. But this is the kind of thing that we use in the probability interpretation of quantum mechanics. All right, and now this is suitable because this says that if modulus of Ca prime square is the probability, then modulus of Ca prime square summed over all the possible measurement outcomes. All right, these are all the possible, this A prime label all the possible measurement outcomes. Okay, so this modulus Ca prime square summed over all the possible outcomes will give you 1. This means that the total probability is equal to 1. So this statement basically says that the total probability for measuring, the total probability is equal to 1. The total probability of all possibilities. All right. If you take each possibility, take the probability of each possibility and add all of them, you must get 1. All right. So the normalization condition that we used earlier, bracket alpha alpha is equal to 1, we'll see later that this boils down to, all right, or this is actually a statement about probabilities. Right? And incidentally, this Ca prime will be called the probability amplitude. Modulus Ca prime square is the probability. Ca prime itself will be called the probability amplitude. All right, or in other words, bar A prime ket alpha will be called the probability amplitude for measuring a particular eigenvalue A prime on the state ket alpha. Okay. Now this last part we'll be discussing again. So I want you to hear it a number of times so that you'll get used to this. Right. So that's why I am mentioning some of the things in advance. Right. If you don't understand it completely, that's fine. Okay. So now what we need here, what you need to take home from this particular slide is just this. Okay. If you have a bracket like this, you can insert, or any legal product for that matter. If you have any legal product, you can insert an identity operator in between, and then this gives us some other kinds of expressions which are very useful. Right. In this case, by inserting this, we get this bracket alpha alpha can be written as a sum of the modulus squares of complex numbers. All right, it can be written as a sum of modulus squares of complex numbers. All right, and the condition that this alpha is normalized, okay, the condition that alpha is normalized actually can be written as this condition. Right, the sum over many real numbers, or sum over the squares of many complex numbers is equal to 1. Okay, so this condition for normalization boils down to a concrete expression of this manner. All right. Now let's look at this, what do you say, ket A prime bar A prime once again. All right, we said that this is an operator, this is an outer product, this is an operator. All right, so it must be an operator. Let's look at its action on the ket alpha. So you take this ket A prime bar A prime and act it on alpha. All right, so you can think of this as the operator ket A prime bar A prime acting on ket alpha, or you can think of this as this number multiplying this ket. Okay, and this number we said is the component of ket alpha in the direction ket A prime. So this is what we denoted as Ca prime, and what do we have here? We get ket A prime bar A prime acting on ket alpha is equal to Ca prime ket A prime. All right, now what is this? Okay. We see that this operator, what's the action of this operator on ket alpha? You get another vector. All right, you get another vector, obviously. So what is the specialty of this vector? We see that ket A prime bar A prime selects that portion of the ket alpha parallel to ket A prime. So for this reason, this ket A prime bra A prime is called the projection operator. Okay, this is called the projection operator along the base ket A prime. All right, now we'll give it a special notation. We'll denote this as lambda, capital lambda A prime. Okay, so we denote this particular operator as capital lambda A prime. So what does this mean? This means that we can write ket alpha like this: C A prime ket A prime plus C A double prime ket A double prime plus etc. Alright. So what we have done here is that we have written this ket alpha as a resultant of different vectors. One vector along the direction ket A prime, another vector along the direction ket A double prime, etc. Alright. Now what does this operator do? If I take this operator ket A prime bra A prime and act it on ket alpha, what do I get? I get this vector. Alright. If I take ket A double prime bra A double prime and act it on ket alpha, what do I get? I get this vector. Alright. So if I do this operator ket A prime bra A prime on ket alpha, I get this vector. And if I do this operation ket A double prime bra A double prime on alpha, I get this vector, etc. So what is this actually? Okay, this vector C A prime ket A prime. Alright. So you can think of this as the portion of ket alpha along the direction ket A prime. Just like in the case of Euclidean vectors we wrote, let me write v vector now. V vector is equal to v1 e1 hat plus v2 e2 hat plus v3 e3 hat. So what have I done here? I have written this v vector as a resultant of three vectors. Alright, resultant of three vectors. One vector along e1 direction, the other vector along e2 direction, and the third vector along e3 direction. Alright, now this we can think of this as the portion of the vector v vector along the direction e1 vector, right? Or the portion of the vector v vector parallel to e1 hat. Alright, maybe it's I'll explain it better with this two-dimensional case. Let's have this two-dimensional space. This is e1 hat, unit vector is e1 hat, and this is e2 hat. We have got this vector v vector. This v vector can be written as a resultant of two vectors. One is v1 vector, the other one, I'll write as v1 vector, and the other is v2 vector. So I am writing v vector as a resultant of two vectors. V vector is equal to v1 vector plus v2 vector. And what is v1 vector? V1 vector is actually this is actually v vector dot e1 hat, the component of, let me write it like this, the component of v vector along the direction e1, okay, multiplied by e1 hat. This is v1 vector, right? This v1 vector. The length of v1 vector is the projection of v vector along e1 direction. That's why I said it's e1 dot v hat. And what's the direction of this vector? The direction is e1 hat. Alright. So this you can think, this v1 you can think of as the portion of v vector in the direction e1 hat, or the portion of v vector parallel to e1 hat. So this is basically decomposing the vector as a resultant of different set of vectors. Alright. Now we could also decompose this same vector. We could also write this same vector as a sum of two other vectors. Alright. You could decompose this along any direction you like. Alright. Okay. So it's the same thing that we do here. Okay. Just like we can say that e1 hat dot v vector e1 hat. Okay, this is a vector which has the direction e1 hat, and what's the magnitude of this vector? The magnitude of this vector is the component of v vector along e1 direction. Alright. So in the same way, we can say that ket a prime ket a prime bra a prime selects that portion of the ket alpha parallel to ket a prime. So ket a prime bra a prime is known as the projection operator. So this operator actually projects. Okay, if I take ket a prime bra a prime, it projects v vector into this direction, right? And it will tell us how much of this vector lies in this direction, right? How much of this vector lies in this direction, right? So that's the reason why we call it as a projection operator, right? Now we had the completeness relation, sum over a prime ket a prime bra a prime is equal to 1, or the identity operator. Right. Now this we denoted as lambda a prime. This means that sum over a prime lambda a prime equal to 1. The completeness relation can now be written like that. Alright. Okay. Let me just summarize what we saw in this class. Okay, we started with the idea that the set of eigenkets of a Hermitian operator forms a basis, forms a set of base vectors. Right? This set of base vectors means that any vector or any ket alpha can be expanded in terms of these base vectors. All right. Now we have this orthonormality property. For this, we said that this is an orthonormal basis. All right. So we have got something like this: bra a double prime ket a prime or bracket a double prime a prime is equal to delta a double prime a prime. This is orthonormality. So we used the orthonormality to show that the C a prime can be written as the projection of alpha in the direction a prime. The projection of alpha in the direction a prime. All right. Now with this we write ket alpha. Using this we wrote ket alpha as sum over a prime. Instead of C a prime I can write bracket bra a prime ket alpha. Okay. Now since this is not legal, I'll be careful and write it like this. Right? This is a number, so it doesn't matter whether I put it on the left or right of the ket. I can take it to this side and write this as sum over a prime ket a prime bra a prime ket alpha. Right? So I've got ket alpha here. I've got ket alpha here also. So something acts on ket alpha, some operator. This is some operator that acts on ket alpha and gives back ket alpha, which means that this is the identity operator. Right? So we get a nice and very useful expression for the identity operator, which is sum over a prime ket a prime bra a prime is the identity operator. Okay, we said this is very important to quantum mechanics. Right? Using this property, we looked at this inner product bracket alpha with itself, bracket alpha alpha, right? And then we inserted an identity operator in between, and we found that this can be written as sum over a prime bra alpha ket a prime bra a prime ket alpha. All right. Now this is nothing but what we have here is the complex conjugate of this, so I can write this as bra a prime ket alpha star ket bra a prime ket alpha. Okay, this is nothing but sum over a prime modulus square of bra a prime ket alpha, right? Or this I can write as sum over the modulus square of the expansion coefficients, because these are exactly the expansion coefficients. Okay, so we saw that this inner product bracket alpha alpha can be written as a sum of modulus squares of the expansion coefficients. All right, this bracket alpha alpha can be written as a sum of the modulus square of expansion coefficients. All right. So the condition bracket alpha alpha is equal to 1 can be written as sum over a prime modulus c a prime square equal to 1. All right. So we said that this is associated with probability, and later we'll call these expansion coefficients as probability amplitudes. Okay. In the end, we defined the projection operator. All right, let me write it here. Okay, we said that this operator ket a prime bra a prime when acting on alpha. Okay, this gives you what is this? This is c a prime. Okay, this gives you c a prime ket a prime. What is this? This is the portion of the vector alpha. It's a portion of the vector alpha, portion of the ket alpha that lies parallel to ket a prime. Right? This is the portion of ket alpha that lies parallel to ket a prime. Right? So for this reason, we said that this ket a prime bra a prime acts as a projection operator, and we said that we can denote it like this. We said that we'll denote it like this: lambda a prime is equal to ket a prime. This was the definition, bra a prime. This is the projection operator. Why do we call it the projection operator? Because it projects the vector, right? It projects the vector ket alpha into another vector, right, which is parallel to ket a prime, right? And what's the significance of this vector? This vector is the portion of ket alpha that is parallel to ket a prime. This was called the projection operator, and in terms of the projection operator, the completeness relation, right? This was called the completeness relation or closure. Completeness relation or closure. So the completeness relation can now be written as sum over a prime lambda a prime is equal to 1. Right? So these are the things that we saw in this class. With that, I'll conclude this session. Thank you.